السلام عليكم ورحمة الله وبركاته. Hello everyone, welcome to our Organic Chemistry 1 class. Today you will continue on Chapter 10, Alcohols. Predict the major products of the following reactions, including stereochemistry where appropriate. R-butane 2O plus tosyl chloride in pyridine. Here is R-butane 2O as a chiral center. This chiral center is not involved in the reaction. The oxygen is, oxygen attack sulfur, break double bond, sulfur double bond oxygen. The oxygen will have a negative charge, go back to sulfur and kicks the Cl out, and the product will be R secondary butyl paratoluene sulfonate. As you can see, the stereochemistry on this chiral center is still R. S2-butyl tosylate with sodium bromide. Here, this chiral center will be attacked by Br as a nucleophile, breaking the bond. This is SN2 mechanism where inversion will occur, and starting with S will lead to the formation of R2-bromobutane. All right. Cyclooctanol with chromium trioxide sulfuric acid mixture, chromic acid. This is secondary alcohol with chromic acid will be oxidized to cyclooctanone, ketone. Cyclobentyl methanol with chromium trioxide pyridine HCl, that's BCC, pyridinium chlorochromate, and this OH is primary. Cyclobentyl methanol with BCC will give an aldehyde, cyclobentane carbaldehyde. Cyclobentyl methanol with sodium dichromate sulfuric acid. Again, this is chromic acid, mixture of sodium dichromate sulfuric will form in situ chromic acid. This is primary alcohol, so it will be oxidized with chromic acid to carboxylic acid, and we get cyclobentane carboxylic acid. Cyclobentanol with HCl zinc chloride. This alcohol is secondary alcohol, so with HCl and zinc chloride catalyst, this reaction will lead to the formation of the chlorocyclobentane and butanol HBr that will take place on this oxygen first protonation, then Br will attack on this carbon to give the bromobutane. Cyclohexyl methanol with Grignard ethyl magnesium bromide. So this carbon with a negatively charged will attack on this H, so it will deprotonate the alcohol to form O- with MgBr to form a salt, and ethane CH3. Okay, this is CH3, and the salt of magnesium bromide. Potassium tertiary butoxide with methyl iodide. This is the butoxide with methyl iodide, SN2 mechanism to give the 2-methoxy 2-methyl-propan, or what we call it tertiary butyl methyl ether. Sodium methoxide with tertiary butyl iodide. Here the methoxide will act as a base, abstracting hydrogen, leaving these 2 electrons to form a double bond, and the iodide will go out as a leaving group, leaving 2-methyl prop 1-ene, what we call it isobutene, as a common name for 2-methyl prop 1-ene. Cyclopentanol with sulfuric acid and heat. Cyclopentanol is secondary alcohol with sulfuric acid and heat, elimination of water to give cyclopentene. Cyclopentene with osmium tetroxide, hydrogen peroxide, then periodic acid. The first step, cyclopentene with osmium tetroxide, hydrogen peroxide, will lead to the formation of 1,2-glycol, 1,2-diol, in what we call it syn addition from the same side. In the second step, this 1,2-diol, this carbon will cleave and double bond in here and double bond in here to give pentane dial, a UBAC name, what we call it glutaraldehyde as a common name. Sodium ethoxide with 1-bromobutane. The ethoxide will act as a nucleophile on the carbon here, kicking this out. It's SN2 mechanism to form 1-ethoxybutane. 1-ethoxybutane, or we can call it its butyl ethyl ether. Sodium ethoxide with 2-methyl 2-bromobutane, the ethoxide here will act as a base and abstract either this hydrogen or that hydrogen, okay, to give the 2-methyl-but-2-ene as a major product and 2-methyl-but-1-ene as a minor product. Why is that? The more substituted alkene, the more stable. So this is a tri-substituted alkene. So, and this alkene is disubstituted. So which one will be more stable? Of course, the tri-substituted. That's why it's a major, or expecting to be the major product. Hexane 1-ol with dimethyl sulfoxide, oxalyl chloride, the mixture we call Swarren reagent, is known to oxidize primary alcohol, that's primary alcohol, to analdehyde, so the product will be hexanyl. And stop. No further oxidation. For cyclopropyl hexane 1-ol, DMB reagent, which we call Dis-Martin periodinan DMB reagent, known to oxidize again the primary alcohol to an aldehyde and stop. Of course, they both Swaran and Desmartin periodinane oxidize the secondary to ketone. In this case, we have here primary alcohol, and it will be oxidized to an aldehyde and stop, and the product will be 4-cyclopropylhexanal. Complete the following reactions. Starting with this molecule, yes, we have here a chiral center, we have here a chiral center, we have the function group is a secondary alcohol. With sulfuric acid, alcohol undergoes elimination reaction to form alkene. So what we expect? We are expecting to get double bond. So this one, or the isomer, where the CH3 will be on that side and the H is up, so we have a mixture of alkene. BCC and BBr3. With BBr3, we get displacement reaction. OH out and Br is in. As you can see, with inversion in configuration, because the reaction will go is in the two mechanism. When the product here react with sodium sulfide or sodium hydrogen sulfide, okay, and again the SH will be the nucleophile, and we get this compound once again is inversion. Inversion is retention. That's why the configuration on this carbon will be the same as that one. Okay? When we react this molecule with BCC oxidation reaction, the secondary alcohol will be ketone. And this is oxidation reaction. To test our skills in synthetic problems, let's try this. Show how you would accomplish the following synthetic conversions. From cyclohexanol to ethoxycyclohexane. By looking to that, this oxygen here is connected to CH2CH3. So how we can replace the hydrogen with ethyl group? If we cut in here, the oxygen will be negative and the carbon here should be positive if you would like to make the connection. If we have carbon positive, mean that we are talking about alkyl halide, where this is partially positive. So starting with ethyl bromide with the alkoxide, here we have an S2 reaction with the formation of ethoxycyclohexane. Alkoxide or alkyl group to form an ether, we call it Williamson ether synthesis. This is very simple problem. Now how we can get from benzyl bromide to 1,2-diphenyl-ethene? Well, if we consider this is this carbon, and we have another one of the same carbon, how we can get them connected to one another? Well, one will say this might come from the alcohol. We have an H in here, We have an OH in here, subject to sulfuric acid and heat, elimination of water, and giving this one. But how we can get this bond together? How we can get it? So we can get this from carbon with a negative charge, and this means that we are talking about Grignard reagent or organolithium reagent with, again, look to this aldehyde. If we get the aldehyde with Grignard reagent, that will form alcohol. Okay, how we can get this one from that one, from the benzyl? Let's just take benzyl bromide with magnesium in ether. You can get this compound. Okay, what about this one? How we can get this from the benzyl bromide? We can get it from benzyl alcohol. And the benzyl alcohol, we can get it from the benzyl bromide. Once again, this is the double bond. Double bond, we can get it from alcohol. Breaking here, this carbon should be negative, this carbon should be positive to make a connection. If this we are talking about, this is negative, this means that we are talking about organo magnesium bromide. Okay, we can get that from the benzyl bromide with magnesium. Okay, what about this one? This carbon should have a positive, partially positive here. We can get this from, and it should, of course, should carry oxygen. So we can get that from carbonyl compound, aldehyde, where we have this partially positive and this carbon partially negative. Okay, if we react this with that, will give us this compound. But how we can get the aldehyde? We can get the aldehyde from the alcohol. And how we can get the alcohol? We can get the alcohol from alkyl bromide, as we are going to see in this one. We get benzyl bromide with magnesium in ether. We can get the compound one. Here is partially negative. We take this one, react it with sodium hydroxide or potassium hydroxide, we get the alcohol. SN2 reaction. Then the primary alcohol with BCC will get the aldehyde, molecule B, where here is partially positive. We react A and B in ether. This will be attacked by the Grignard. Open this one, form the salt, hydrolyze it, give it the alcohols. The alcohol with sulfuric acid and heat, we get the final target molecule. Easy and straight forward to some extent. Here we would like to transfer cyclohexanol to 1-bromo 2-methyl-cyclohexane. If you look to the molecule, target molecule, find here Br, and this carbon has an H. We can get this molecule from alkene. Remember that this carbon has an OH, right? Okay, we can get the alkene from alcohol by dehydration. Okay, here if we put the OH in here and CH3 in here, fine, we can get that from carbonyl and Grignard. Ketone and Grignard gave you tertiary alcohol. That's acceptable. And the ketone, we can get that from alcohol. That's our starting material. So our starting material, upon oxidation with any of the reagent we know chromic BCC, colon reagent, whatever, we can get the ketone. Reacting the ketone with methyl magnesium bromide in ether, followed by acidification, we can get that alcohol, right? Dehydration using consulfuric and heat, we can get the alkene. Now we would like to add the HBr. The H will be added to the carbon carrying list. This has no hydrogen, and this carbon has one hydrogen. So it is anti-Markovnikov. How we can add HBr anti-Markovnikov? We use HBr in presence of peroxide. Peroxide will make this reaction use anti-Markovnikov, and we can get the target molecule. No problem. Okay? How we can get from but2ol to this species, epoxide? Well, if we look carefully for this carbon, it carries CH3 and the ethyl group. Here is this carbon carries methyl and the ethyl group. This is in epoxide functionality. We can get the epoxide functionality from alkene. We can get the alkene from alcohol by dehydration. We can get the alcohol by reacting carbonyl ketone with Grignard. If we cut here, this one will be the carbonyl and this one will be Grignard. And the ketone, we can get it from the alcohol. Yes, we can do that. Here is but2ol. Upon oxidation will give butane-2-on. Reaction of this carbonyl compound with cyclobentyl magnesium bromide, Grignard reagent in dry ether, followed by acidification, will lead to the formation of this alcohol. Dehydration, elimination of molecule of water using sulfuric acid and heat would give this alkene, which upon reaction with metachloroperoxybenzoic acid will lead to the target molecule. I hope you have enjoyed this session. Looking forward to seeing you in class. Bye bye.